Hello everyone and welcome to my lesson on parallel circuits. If you pause the video you can have a go at the quick quiz and the answers will be on the next slide. Give your answers a tick if they're right. If they're wrong, write in the correct answer. Okay, today we're talking about parallel circuits. Everything we've done so far in electricity, so we've talked about current, voltage, resistance, power, everything so far, energy transfer, has all been related to series circuits. Now, it's kind of the same for all electrical circuits, of course, but we've only talked about series circuits until now. So we've used V equals IR, we've used Ohm's law, everything has been about a series circuit. So now we're going to look at parallel circuits, but we're going to use the same models to explain it. Now they're the models we've used before, so we know what they look like. We know what they look like in our heads, and we can use those to see how parallel circuits work. Just a quick recap of the model. The model of this one looks like a pipe with some peas in it. There's a treadmill at the top and a paddle wheel at the bottom. Now, as the hamster runs in a treadmill, he pushes those peas around. He gives energy to the peas, and all the peas move in the pipe. They all sort of move together. And as the peas move around the pipe, they'll push the paddle wheel at the bottom. And the paddle wheel turns round. And you could say that the peas give energy to the paddle wheel, and then the peas carry on moving. In exactly the same way, in electrical terms, this cell at the top gives energy to the electrons. The electrons move around a wire, and then the energy of the electrons gets transferred to the component. So it's to the light bulb or to the heater or to the motor or something. And then the electrons carry on around the wire until they gain more energy at the cell again. This was the second model we used. The plates were going around on a conveyor belt. At the top, they picked up biscuits from the packet of biscuits. The plate carried on around the conveyor belt, and then the baby ate the biscuits, and the plate carried on going around the circuit. Now, in electrical terms, each plate is a coulomb of charge. So down the bottom here, this plate here would be a coulomb of charge. This plate here would be a coulomb of charge, and etc. All of them are 1 coulomb of charge. Each plate has got 12 biscuits on it. Therefore, each coulomb has got 12 joules of energy on it. This one's got 12 joules of energy on it. This one's got 12 joules of energy on it. Now, if there's 12 joules for every coulomb, this would be 12 volts. And we would call that potential difference. And that's why we put our voltmeter on each side of the light bulb, like this, because we're measuring the difference on each coulomb. So here there are 12 biscuits on this plate, and there are no biscuits on this plate. So the difference, the potential difference, would be 12 volts. Now these are the two models we've used before. We've used them quite a lot, so we're going to use these exact models for the next stage to explain a parallel circuit. Just to recap the series circuit, we're going to do current in a series circuit. The rule for current in a series circuit is that the current is the same everywhere. Current is the same everywhere. For example, if I had, let's say, 12 amps coming out of here, then I'm going to have 12 amps coming here, 12 amps going through here, 12 amps going here, and 12 amps going here. It's a series circuit. They can't go anywhere. So current is the rate of flow of charge. It's the amount of coulombs every second. And using the model, these P's can't go anywhere. If there's 12 P's passing this point up here every second, then there's going to be 12 P's passing every point in a second. Otherwise, you'd end up getting a build-up of P's somewhere. or a big gap. You can't have that. So for a series circuit, current is the same everywhere, and that's because the P's just can't go anywhere. They're in a closed loop. They're in a circuit. The rule for potential difference in a series circuit is this. If we started with 100 volts up here, just imagine. So that's a bit like the plate gaining 100 biscuits. Now the plate might travel down here, and when it comes to this lamp, it might lose 20 biscuits. If it lost 20 biscuits, I would say that's 20 volts, 20 joules per coulomb. And then it might lose, when it goes through the resistor, the second one, it might lose 50 biscuits, or we'd call that 50 volts. And that means there's 30 biscuits left. If we lost 20 and then we lost 50, there'd be 30 left. And the rule is that every biscuit must go. So for potential differences in a series circuit is that every single potential difference must add up to the cell. So 20 plus 50 plus 30 adds up to 100. And that's the rule for potential difference in a series circuit. Now we come into the parallel circuit. So we know it's parallel because the two components are next to each other, like parallel train tracks. They're not one after the other. And I want you to imagine that we've got our plates traveling down here. Now, if you notice just here, I'm colouring it in now, just here there's a junction. Now, when those plates get to the junction, they must split up. We're going to have some going down this way and some going down this way. Now, it doesn't have to be, if we started with 4, it doesn't have to be 2 and 2. It could be 3 and 1. It could be anything. But it does split up. And that's the rule. Whatever current goes into a junction, so here we had 4 amps going into a junction, whatever it does, it splits up. It must equal exactly the same as what went in. So the rule is whatever current goes in a junction is the same current that comes out of a junction. So this, in our example, was 4 amps, and that split into 2 and 2. It could have been 3 and 1, or 3.5 and 0.5. It could have been anything. But the rule is whatever goes into a junction must come out of a junction. And if we follow this all the way, we're still going to have 2 amps over here. If you follow this all the way around, we're still going to have 2 amps going up here. And there's another junction. So if we've got 2 amps going in and 2 amps going in, then we're going to add up to 4 amps. It's the same rule. The 2 amps and 2 amps go in, and the 4 amps come out. So the rule for current in a parallel circuit is that the current into a junction is always equal to the current out of a junction. Okay, I'm going to do one more example, exactly the same thing. We've got 10 amps flowing down this wire here. So 10 amps going down here. And we come to a junction. Let's just imagine for now that we have 1 amp going off to the light bulb here. This depends on the resistance. Then we're going to have 9 going this way. Now these numbers will get given, or you can calculate using V equals IR. So the more resistance that this bulb has, the less current it would have. But here we can say that 9 amps goes down here, and then we come to another junction. And we might have 5 amps going this way and 4 amps going this way. And then there's still 4 going this way. And there's still 4 here because it's still in the same part of the loop, so it goes around here. But there's a junction just here. Just here there's a junction. And 5 and 4 add up to 9, so it would be 9 just here. And this 1 and this 9 add up, and it'll be 10 amps over here. So it's exactly the same rule. Whatever the current into a junction is exactly the same as the current out of a junction. So just to put them side by side, we're going to do series on the left, parallel on the right. Here, if I had 10 amps, that's like using the model 10p's flowing every second. They can't go anywhere, they're in a closed loop, it's the same everywhere. 10 amps everywhere. In parallel, it's slightly different. If I had 10 amps going here, I might have 7 amps going through here and 3 amps going through here. Now they'll always give you one of them, you'll have to work out the other one. And then 3 would carry on down here, and then those would add up at the junction to make 10 amps up here. So there's your series on the left, parallel on the right. If you want to, you can pause the video, write this down from memory, and then check yourself if you want to. Okay, questions. Have a go at these, and we'll go through the answers in a second. Okay, answers for a series circuit. The current is the same everywhere. If we had 5 amps in this circuit, it would be 5 amps everywhere. And in parallel, if we had 12 amps going down here, the current into a junction is exactly the same as the current out of a junction. So 10 and 2 add up to 12. And if you think about it, it's just about thinking about the P's. The P's have to split up when they come to a junction. If I had 12 P's, I'd have 10 and 2. I can't have more than 12 P's. I can't have less than 12 P's. They can't go anywhere. There's 12 amps up here. So there's your rule. Current in a series circuit and current in a parallel circuit. Okay, next we're going to have a look at potential difference in a parallel circuit. Now, we're going to start off exactly the same way. We're going to start with these plates coming down the conveyor belt. They come to a junction here. They come to a junction. Now we know that they're going to split up. It could be 3 and 1, 2 and 2. It doesn't matter. They're going to split up. That's the current. But the potential difference is to do with the biscuits on a plate or the joules on a coulomb. How much energy that coulomb has. Now you can see that if we started off up here with 12 joules on every coulomb, over here we've still got 12 joules on every coulomb. Just here, there's 12 joules in there, there's 12 joules in there, 12 joules in here, and 12 joules in here. So when that plate goes through the light bulb like this, it's going to lose all 12 and then carry on over here back to the cell so it can pick up more energy. So the difference between this point here and this point here was 12 joules per coulomb, or 12 volts. And then this plate carries on. It's also got 12 joules on that coulomb. It carries on down here with 12 biscuits on it. It goes through the resistor And again, it comes back with nothing and then goes back to the cell. So therefore the difference, if I put a little voltmeter here, the difference with this would be 12 volts. And you can see that with the biscuits. If I lose all the biscuits, then I've lost 12 joules per coulomb here. I've lost 12 here, and therefore they go back empty. All plates have to go back empty, because then they can pick up 12 more biscuits over here. They can pick up 12 biscuits here. If they didn't go back empty, there'd always be an accumulation. They'd sort of get more and more and more and more and more and more, and they can't do that. Okay, let's use some numbers. So it's straightforward. If this is 230 volts in the cell, then everything in a parallel circuit is 230 volts. And it's exactly the same reason, because the electrons here, or the coulomb of charge here, splits up. So if we had 2, we might split up here. But the amount of energy on each coulomb, here and here, is going to be the same. So therefore it's 230 volts for every component in a parallel circuit. Okay, I'm going to compare these now. So I've got series on the left and parallel on the right. If I had 100 volts here, then the rule is that these split up. Both of these potential differences add up to the cell. That's the rule. Now, they'll give you one of them. So it could be 10 and 90, 50, 50, 60, 40. It doesn't matter. They'll give you one of them and you've got to work out the other. And in parallel, if this was 100 volts, then this light bulb would be 100 volts and this resistor would be 100 volts. So in series, the potential difference splits up. And that's because, that's quite obvious if you think about it. This plate over here with biscuits on has to lose some biscuits through the first bit and then some through the second bit. So it's lost 20 through the first and then 80 through the second. But here, these biscuits split up and they've got the same. So the amount going through this resistor is the same as the amount going through this bulb. And that is potential difference in series and in parallel. Pause the video, have a go at writing what we just talked about, and then I will put my answers up on the next slide. I'm going to go through the answers on this slide. It doesn't matter what numbers you use, as long as the principle is still the same for each circuit. So I'm going to use the example of 50 volts here, and I'm going to say that there was 5 volts here and 45 volts here. They both add up to 50, so as long as both of yours add up, that's okay. If I had another component, by the way, let's say I put another component in here, then all 3 would add up to 50. So therefore these two would have to go down a little bit, because all 3 would add up to 50. But we won't do that. And then for this one, we're going to have, let's say, 150 volts up here. Then everything in the circuit would be 150 volts. Pause the video and write down as many equations in electricity as you can. I'm going to go through a few that I can remember. I know that current is the amount of charge per second. Now we might write this one as Q equals IT. Those two are the same equation. What we're thinking is current is coulombs per second. Or we use this current, which is coulombs per second, times by the number of seconds. For example, if there was, say, 3 amps, 3 coulombs per second, and we times it by 10 seconds, there's obviously 30 coulombs have passed. We've also got the most important equation in electricity, V equals IR. So potential difference is current times resistance. We've also got P equals IV, power is current times potential difference. There's another one for power, which is I squared R. If you can't remember these, there's a video for this if you want to. There's another one for power. Power is energy per second. So the amount of energy going to a component every single second, that is your power. So energy per second. And the last one, we know that the energy in a circuit is the potential difference, which is the joules per coulomb. Joules per coulomb, that's what voltage is, joules per coulomb, times by the number of coulombs, and you'll get joules. So there was 5 joules per coulomb, and we've got 10 coulombs. Well, that's 50 joules in total. Or using the model, we could have 5 joules per coulomb. That's 5 biscuits on each plate, and I've got 10 plates in total. Oh, that'd be 50 biscuits in total. So these are the equations you need to memorize. We're going to use some in the next slide. I'll show you how to use them first, and then there's a worksheet which will be in the description, which you can have a go at. Pause the video, have a go at the questions on the board. If you can't do them, don't worry, my workings and answers are on the next slide. Question number 1. What is the potential difference of the resistor? Well, I'm going to draw this in blue. We know that if it's a parallel circuit, the cell has a potential difference of 20 volts. Therefore, the bulb would be 20 volts and the resistor will be 20 volts. So it's 20 volts. What's the potential difference of the bulb? Same as the cell, 20 volts. What's the current flowing through the bulb? The current flowing through the bulb. Well, I can see that down this branch here, we know there's 5 amps. And I know that 2 amps have gone down this branch because it's down here. So if 2 have gone this way, I know 3 amps would have gone that way. So the current flowing through the bulb is 3 amps. What's the power of the light bulb? The power of the light bulb. What do I know about the light bulb? I know that the potential difference is 20 volts. I know that the current is 3 amps. And I want the power. Draw a line. So our equation that's got potential difference in it, current in it, and power in it. P equals IV. If you don't know them, try and memorize those equations. P equals IV. P equals I, which is 3, times V, which is 20. So therefore the power is 3 times 20, 60 watts. So the answer is 60 watts. Question 5. What is the power of the resistor? The power of the resistor. So what do I know about this resistor? Should we do this one in purple? Yeah. We know that the potential difference is 20 volts. We know the current is 2 amps. Power in the resistor is not sure. So same equation, P equals IV. I don't know P, leave that as P. I do know I. I is 2, written over here. And I do know V, written over here, so that's 20. So power is 40 watts. Last one we're going to write in, oh, hang on a minute. Power of the resistor is 40 watts. Last one we're going to write in green, question 6. How much energy flows through the bulb in a minute? How much energy flows through the bulb in 1 minute? What do I know about the bulb? I know that the potential difference is 20 volts. I know the current is 3 amps. And it's 1 minute. The time is 1 minute. But alarm bells are ringing right now because 1 minute is not right. We can't have minutes, not in physics. So I've got to straight away turn it into 60 seconds. And that's okay. And the question was how much energy flows? How much energy flows? Is there an equation that's got some of these in it? Well, the question is how much energy flows. Oh no, I do know power of the bulb, don't I? I worked it out up here. What's the power of a light bulb? Just up here, so I know the power is 60 watts. Now there is an equation with power. It's power, energy, and time. So power is energy divided by time. Now recognizing that equation is a little bit tricky, but if you've memorized all your equations, you should be able to look and go, oh, I know one with energy in it. I know one with power in it and time in it. You definitely knew time was in it because of this, and you definitely knew energy was in it because of this. So energy and time powers the missing link. So put it in the words, the numbers we know. The power is 60. The energy is what I'm looking for. And the time is 60 seconds. So it's 60 watts for 60 seconds. Now, if that's divided by 60, I've got a times by 60 on this side, and that will get rid of that 60. And times by 60 on this side. So this side, those two cancel, so we end up with energy. And on this side, I've got 60 times 60, and I can use my calculator. 60 times 60 is 3,600 joules. That's how much energy went through the bulb in 1 minute. Okay, question number 7. Question number 7. So we start with the potential difference of the diode. Well, I know that if that's 110 volts, then every component in a parallel circuit is 110 volts. So the answer is 110 volts. What is the potential difference of the resistor? Well, that's also 110. It's a parallel circuit. Everything has the same. The current flowing through the ammeter. Well, I know that there's 1 amp flowing up here. There's 6 flowing here, and there's 3 flowing through here. So that 3 that flows up here hits a junction, adds with a 6, and makes 9 amps here. And then the 9 and the 1 add up at this junction, and that makes 10 amps going through here. So the answer is 10 amps. Remember, for current, the current flowing into a junction is the same as the current flowing out of a junction. What is the power of the diode? The power of the diode. Well, let's have a look. Question number 10. Power of the diode. Where's the diode? Diode's down the bottom. I know that the potential difference is 110 volts. I know the current is 3 amps. And I'm looking for the power. Draw a line. P equals IV. You've memorized this. P is I know what I is 3, times V, which is 110. Use a calculator, I'm going to do 3 times 110, 330 watts. Very good. Question, I'll write that in, 330 watts. Question 11, what's the power of the resistor? Exactly the same question. So I know the potential difference of the resistor is 110. I know the current of the resistor is 6. Power is question mark. So therefore power is IV. Power is I times by potential difference, which is over here. So there's my I and there's my V. Therefore power is 6 times 110, use my calculator, 6 times 110, 660 watts. 660. Question 12, how much charge how much charge flows through in 10 minutes? 10 minutes. How much charge flows through in 10 minutes? Question 12. So question is how much charge? Time is 10 minutes, so 10 minutes. Alarm bells, 10 minutes in seconds. So 60 seconds in a minute times that by 10 minutes is 600 seconds. 600 seconds. Now there's an equation here. I'm looking for charge, Q and T. The missing thing I need is I. So the I for the bulb is 1 amp. Draw a line. Q equals IT. The charge is equal to I, which is 1, times T, which is 600 seconds. So therefore the charge is 600 coulombs. Boom. Last one. What is the resistance of the resistor? Question 13. So I'm looking for the resistance of the resistor. What do I know about the resistor? I do know that the current flowing through it is 6 amps. I do know the potential difference is 110 volts. Now there is an equation that links these, V, I, and R. The equation is V equals IR. Put in the numbers we know. I know V is 110. I know I is 6. I know R, I don't know R, so I leave that as R. Now if that's times by 6, I need to divide both sides by 6. So this side, because that's times by 6 and divide by 6, this side is just R. And this side is 110 divided by 6. So I'm doing that on the calculator. 110 divided by 6. 18.3. 18.3 ohms. So the answer is 18.3 ohms. And the question above, 600 coulombs. Very good. There's my workings. So what I'd like to do now is in the description, there's a link to a worksheet on parallel circuits. I'd like you to have a go. If you get stuck, you can send me an email and I'll help you. There's also a link on the Google Classroom to the worksheet which you can have a go at. Good luck, and I'll see you next week for the next lesson.